Yeah. So hi, I hope I'm audible. I'm Catherine Functioner, a PhD scholar from IIT Madras. I'm working under the guidance of Dr. J. Krishna. So this is a tutorial session which will be held every Tuesday between 6 p.m. and 8 p.m. And if you have any queries, you can. This video will also be posted in YouTube. The link for which will be provided by the NPTEL. So if you have any queries, either you can post in the discussion forum in the NPTEL website, or you can comment in the below the video, below the YouTube video. So without any further delay, we will start. We will begin with the session. Okay. So let me share my screen. Yeah, I hope my screen is visible. So first, I will begin with deriving a few viscoelastic models, okay, which has been explained by Sir, and later we will be moving on to um, solving some previous year's assignment questions. So first, we will begin with the Maxwell model. Okay, so you know what a Maxwell model is. So first, you know what a viscoelastic material is. Right? A viscoelastic material has been hypothesized as a material with viscous effects and elastic effects. Right? Now, to represent these components in the form of a model, they've adopted few elements, basic elements, which could describe the properties of a viscoelastic material. So, to bring out the elasticity of the material, they proposed to use a spring. Okay, and to bring out the viscous nature of the material, they have proposed to use a dashpot, okay, with a material parameter called viscosity, and this will have a material parameter called as modulus. The spring will have a material parameter called as modulus. Now, by arranging these two elements, okay, in series or parallel, in any number, in any combination, a few viscoelastic models have been explained, okay, three of which will be seen in this class. So, in a Maxwell model, these two elements are arranged in a series. Okay, so let us represent the modulus of the spring as R1 and the viscosity of this dashpot as eta 1. So, um, you know what, since a spring is an elastic element, it it obeys the Hookean um, response, right? So if you try to write the equation for the if you try to write the stress strain equation for a spring, you will write it as modulus equals to sigma by epsilon, right? Where sigma is the stress exerted on this spring and epsilon is the strain due to the deformation undergone by the spring. And similarly, a dashpot is a viscous element, and so it will have a property called as viscosity. And for a viscous element, okay, the stress strain relationship is given by stress divided by strain rate, right? Okay, here I'm not making any distinction between whether it is a shear stress or normal stress. I'm simply representing this as sigma. Okay, if it is a shear stress, I will represent this as tau. Okay, and similarly, if it is a axial strain, I will represent it as epsilon, and if it is a shear strain, I will represent it as gamma. Okay, so here I'm not considering whether I'm applying a shear stress or normal stress. I'm just using these notations. Okay, so in a Maxwell model, these two elements are arranged in parallel. Sorry, series. Now, if I apply stress to this element, okay, this spring will undergo a deformation, okay, and let us say that the strain undergone by this spring, let this be denoted as epsilon s, since this is a spring, and the deformation, the strain due to the deformation undergone by this dashpot, let us denote it as epsilon d. So what will be the total deformation undergone by the material, or the total strain undergone by the material? It will be epsilon is equal to epsilon s plus epsilon d. So this is the total length, total deformation that the entire Maxwell element would have undergone, right? But what will be the stress exerted on each of these elements? It will be simply sigma, okay, which means the stress that is exerted on the spring, which is sigma, which can be denoted as sigma s, is equal to the stress that is exerted on this dashpot, which can be denoted as sigma d, which is nothing but the stress that I'm exerting on the total Maxwell model. Okay, so sigma s is equals to sigma d is equals to sigma. Now I have to develop a constitutive relation for this Maxwell model. So what do I mean by a constitutive relation? Any equation that relates stress and strain is called as a constitutive equation. Now, since we are all aware of um, we know structures better. Okay, we know elasticity better. I will give you an example of a constitutive relation which we all know. Okay, or these two relations are nothing but constitutive relations, because this is an equation relating stress and strain for a spring which is an elastic material, and this is a equation relating stress and strain for a viscous material. Okay, so these two are nothing but constitutive relations. In the same, so an elastic material is modeled as a spring and the viscous material is modeled as a dashpot, and the constitutive relations are given as such. Okay, in the same way, a Maxwell model also need to have a constitutive relation, right? So it needs to have an equation which relates stress and strain, so that if at all, so why do you need this constitutive relation? Let us say I have a steel bar and I am applying some force to it. Okay. Now I know that steel is an elastic material. I'm modeling steel as an elastic material, and I know the constitutive relation. I know that it obeys Hooke's law, and so I write Young's modulus as stress by strain. Okay, since from force I can determine stress, and since I knowing the modulus of the material, okay, I can determine what could be the response of the material. The response which I'm talking about here is the deformation undergone by the material. So if I'm applying force, I can um, calculate the deformation, okay, by making use of this model. Or if I'm applying some deformation, some known deformation to it, okay, delta, I can find out the stress that the material has been put through. Okay, so for this we need constitutive relations. Okay, so this is for an elastic material. In the same way, for a viscoelastic material, so if we are modeling it as a Maxwell model, then only if we have the constitutive relation we will be able to find out the stress or strain response. Okay, now, so let us see how to derive this constitutive equation. So we already saw that epsilon is equals to epsilon s plus epsilon d, right? We know what epsilon s is. From from the spring, we know that epsilon s is equals to sigma s divided by r1. What is sigma s? Sigma is nothing but sigma, right? Since sigma is the same. So sigma divided by r1 will be my epsilon s. What is my epsilon d? Okay, so first let us first write the equation for viscosity. Eta 1, okay, it need not be eta 1 since I have only one viscosity, one dashpot and one spring, it can simply be eta and r. It need not be 1. You need not write the subscript 1. Okay. So eta is equals to sigma d divided by epsilon d dot. Right. So from this I can get epsilon d dot as sigma d divided by viscosity. Right. Now I know what epsilon is. So since I have uh, epsilon dot here, okay, I am going to write this entire equation. I'm going to write this entire equation in terms of derivative. Okay, I'm going to uh, differentiate the entire equation by t. Okay, so epsilon dot is nothing but d epsilon by dt, right? So now epsilon dot is equals to, so if you see here, this epsilon s will become epsilon s dot will be sigma dot divided by r. Okay, so this will also be sigma divided by eta, since sigma d is equals to sigma. Now epsilon dot is equals to, what is epsilon s dot? Sigma dot by r plus sigma divided by eta. Okay, now this is my constitutive equation. Why am I calling it as constitutive equation? This relates stress and strain. It can be stress and strain, or stress, derivatives of stress with strain and derivatives of strain. So this equation relates stress and strain. So this is my constitutive equation. Okay, now I have this constitutive equation. So how is this constitutive equation useful to us? How is it going to be of use to us? Okay, so we know two cases. Okay, we have heard of, so I told you, given a deformation, we can find out the stress that has been that the material is subjected to, or given a stress, we can determine what the strain that the material is subjected to, right? So for that, let us first give a constant deformation to the material. Constant deformation or constant strain to the material. So this is what I'm going to apply to the material. Now, how will I find out the stress response? So if I'm applying strain, the response of the material will be in terms of stress, right? So this is a constant stress. So with T, my constant strain. So with T, my strain is going to remain constant, right? So now, what is this called as? We've seen this in the earlier classes. This is called as a stress relaxation experiment. Right? Now, let me apply this condition to the equation. So this is my constitutive equation plus sigma by epsilon by eta. Right? Now, in this case, what do you think will be strain rate? So this is what I'm controlling, okay? So if I'm controlling the strain, I know the equation of strain. So I can simply substitute the equation of strain in the constitutive equation. Now I'm subjecting the material to a constant strain, which means my strain rate is equal to 0. So in this equation, I can simply substitute epsilon is equals to 0. So which will give me sigma dot by r plus sigma by eta is equals to 0. Now this is the differential equation which I have to solve. So if you see, if I solve this differential equation, what is the solution of a differential equation? You know that if you have, let us say you have a normal equation, say y is equals to 2x. Okay. So given a value of y, given a value of x, you can find out y, right? So if you have to solve a differential equation, the solution of the differential equation will be a function. Okay. So how do I say this? Now this is a differential equation in stress. This is what I have to find out. What did I tell you when we first started to derive? I said that given a strain input, I have to find out the stress response, right? Now this stress response is a function of time. Why is it like that? We already saw that viscoelastic material is a time dependent material. So even if I'm going to apply a constant strain to the material, my stress is going to vary with time. That is why this equation has to be solved. So if I solve the differential equation, I will get the response of the material as a function of time. Okay, so this is what I want. So what is the differential equation that I have to solve? It is sigma dot by r plus sigma by eta is equal to 0. Right? Now let me write this as d sigma by dt into 1 by r is equals to minus sigma by eta. Okay. So now how am I going to solve this? I'm going to solve this by separation of variables. Okay. So I'm going to bring all the sigma to one side, okay, into 1 by r is equals to minus 1 by eta into dt. Okay. So now I'm going to integrate this. So what will I get? Ln of sigma into 1 by r is equal to minus t by eta, or I can write this as plus ln of c, right? Why have so I'm integrating it, and this is without any limits, right? So I have to introduce a constant, integrating constant, and a boundary condition to solve this constant, right? So since this is a ln, I am introducing this constant as also ln c. Okay, no issues. Now 1 by r into ln of sigma is equals to minus t by eta plus ln of c. So what is the boundary condition? Only if I have a boundary condition, I can solve for this equation, right? Since this is a first order differential equation, why is it a first order differential equation? It has only d sigma by dt. Okay? So since this is a first order differential equation, I will have only one boundary condition, and that boundary condition will be, how will I find out the boundary condition? So we saw earlier that when a viscoelastic material is subjected to a constant um, strain, okay, the response will be like this, right? So at time t is equals to 0, my stress will be equal to sigma naught. Okay, and what is the sigma naught? The sigma naught is the response of the spring, okay, which will be r into epsilon. Okay, since this strain is constant, I will represent this constant strain as epsilon naught. Okay, so this response will be r into epsilon naught. Why am I saying that at time t is equals to 0? So this Maxwell element has both a spring and a dashpot, right? So at time t is equals to 0, when I apply a strain of epsilon naught, then I should expect stress in both these elements, right? Why am I Why am I saying that at time t is equals to 0, the contribution of the response will be only from the spring? It is because when I apply a deformation to the material, okay, when we saw the properties of an elastic material, we saw that when I apply a deformation, if it is an elastic material, it will immediately deform, right? So both will have a constant value. In the case of a uh, viscous material, it will have a delayed response. Okay, so at um, Okay, sorry. It will have it needs to have a uh, infinite stress at time t is equals to zero, right? So, when I apply a strain to the material, the first thing to deform will be my spring. Okay, the dashpot will take some time to deform. It will deform only after time t is equals to zero. Okay, it will take some time. So at time t is equals to zero, the contribution of the strain will be only from the spring. So that is why at time t is equals to zero, sigma dot, the stress in the material, or the stress at time t is equals to zero, will be only from the spring. Okay. Now I have to substitute this boundary condition in this equation. In this equation. Okay. So it will be 1 by r into ln of sigma naught. Okay. I'll replace for the sigma naught later, is equals to, at time t is equals to 0. So t is 0, this term will vanish. 0 plus c. So c is going to be 1 by r into ln of sigma naught. Now let me substitute for this. Sorry, ln of c. This is ln of c, right? Ln of c is equals to 1 by r into ln of sigma naught. Now let me substitute for this ln of c here. So 1 by r into ln of sigma is equals to minus t by eta plus 1 by r into ln of sigma naught. Okay. So let me take it to the left hand side. So 1 by r into ln of sigma minus ln of sigma naught is equals to minus t by eta ln of sigma minus ln of sigma naught is equals to minus r into t by eta. So this, I can use this division rule, right? So ln of sigma minus ln of sigma naught can be written as ln of sigma by sigma naught minus r into t by eta. And this ln, if it goes to the other side, it will become exponential, right? So it will be e power minus r into t by eta. So sigma is equals to sigma naught into e power minus r into t by eta, right? So this I can substitute for the sigma naught as r into epsilon naught into e power, or it can be sigma naught, no issues. Okay, so this will be my sigma of t when, or this will be my stress response when my Maxwell model is subjected to a stress relaxation test, or when I'm predicting the material response using a Maxwell model by subjecting it to a stress relaxation test. Okay, so this is my sigma of t. Now, let us say I'm subjecting the material, I'm subjecting the material to a constant stress. Okay, now what should I find out now? The response of the material will be strain. Okay, so I have to find out the variation of strain with time. So now, so if I plot this, okay, plot this response, how will it be? So this is my epsilon t, epsilon naught is what I'm subjecting the material to, and this will be my stress response. Okay, it will be like this. Okay, so this is what this equation says. Now I'm subjecting the material to a constant stress. Okay, so what will I call this as? This is a creep experiment. So whenever I'm subjecting the material to a constant stress and measuring the deformation, I will call this as a creep experiment. So let us say this sigma value is sigma naught. Okay, I'm applying value of sigma naught with a constant time. Okay, throughout. Now, how will I find out the strain response of the material? So let us say, uh, okay, let us say, so what is my, so now what should I do? This is my constitutive equation. I should substitute for stress values, okay, in this equation. So let me go and write the constitutive equation first. Sigma naught divided by sigma dot divided by r plus sigma divided by eta. So this is my constitutive equation. I have to, right? So in this equation, this sigma dot is 0. Why is it 0? I'm substituting the material to a constant stress. When I'm substituting it to a constant stress, then derivative of that stress will be 0, right? So, and this will be equal to sigma naught, okay? Sigma is equal to sigma naught. So I'm substituting these values, and this is what I get. Now I'm writing this epsilon dot as epsilon d epsilon by dt is equal to sigma naught by eta. So here also let me separate the variables. Okay, and now I'm integrating this. So this will be epsilon is equal to sigma dot by eta into t plus c, my integrating constant. So to solve for this integrating constant, I need a boundary condition, right? So what will be the boundary condition here? Here also, it will be the spring to respond first. Okay. So when I'm subjecting the material to a constant stress, my spring responds first, which means my epsilon will be equal to sigma naught by r, which is the strain, the entire strain at time t is equals to 0 will only be because of this strain in the spring. Okay, and this strain in the spring can be represented by sigma sigma dot sigma naught divided by r, right? So at time t is equals to 0, epsilon is equals to sigma naught divided by r. Okay. Now one more thing is, ah, so this is fine. So let me substitute in this equation. So epsilon is equals to sigma naught divided by eta into t plus c at t is equals to 0. Epsilon is equals to sigma naught by r. So sigma naught by r is equals to sigma naught by eta into t. Sorry, this will be 0 plus c. So epsilon of t. Okay, so this is a function now, right? It is a function of time by eta plus sigma dot by r. So this is my strain response with time when the material is subjected to a constant stress. Right? Now let us see how this strain will look like. So this is my time and this is my stress, and I'm subjecting the material to a constant stress of sigma naught. Okay, so let us see how the response will look like. So how will I plot this response? I know the equation, so let me see what is the value at time t is equals to 0. At time t is equals to 0, this term will vanish, so my strain will only be because of this spring, which will be sigma naught by r. So this will be my sigma naught by r at time t is equal to 0. Now, this is a linear equation, right? It is a linear equation in t. So, from sigma naught divided by r, so this is my, so So this is my intercept. Okay, so intercept is the y value at time at t is equals to 0, and after that the strain increases with the slope of sigma dot sigma naught divided by eta. Okay, so this is my slope, right? So it increases with a value with the slope of sigma naught divided by eta. Okay, so what is the sigma naught divided by eta? So what is the slope? Sigma naught divided by eta. Now this sigma naught, so this is the slope, right? What is the slope of a strain curve? It is nothing but strain rate. Okay, so it increases with a constant strain rate. Since the slope is constant, the strain rate is a constant, right? So let us say, so this is the response. Now let us say at time t1, so this is the response when I'm subjecting it to a constant stress. Now let us say that at time t1, okay, I am going to remove this stress. So how will you represent this as? You know that using the principle of superposition, I can split this into two. One will be, I will subject this and material to a stress sigma naught for the entire duration of t. Okay. Now at time t1, I have to subtract the sigma naught, only then it will become 0, right? So from t1, I will apply a stress of minus sigma naught. Okay. So if I add these two up, okay, if I add these two up, I will get this this figure, right? So now how will the response be? Okay, till time t is equals to t1, it is going to be like this. Okay. After time t is equals to t1, it has to be a superposition of these two, these two um, stress inputs. Okay, so let us write for t greater than t1, how the response is going to be. Okay, till t less than t1, this is the response. Okay. So for t greater than t1, it is going to be a superposition of these two. Okay, which means I need to find out the response somewhere here. So it has to be a superposition of these two. So how will I represent this? It is going to be, so epsilon of t. Okay, at any time t it is going to be equal to epsilon of t plus epsilon of t minus t1. Sorry, uh, uh, epsilon of t minus t1. Okay, this is subjected to a stress of sigma dot, and this is subjected to a stress of minus sigma dot. This one is okay. So why am I saying this? So if you see, this is for the first term. Okay, I need response at time t. So this is going to be, and I have to find out the strain value. Okay, as per this equation, when subjecting the material to a stress of sigma dot. Now, this plus I have to add this the response due to this stress also. Only then I will get the response due to this recovery part. Okay. So now, if you see this portion, I'm applying a stress of not sigma dot, but I'm applying a stress of minus sigma naught. Okay. So here it will be again, and it starts only from time t1. Okay, so this is my time t. I'm applying, so this strain response starts only from t1. So here it has to be epsilon of t minus t1. Okay, so and this when it is subjected to a stress of minus sigma dot. Okay, here it is not being subjected to the same stress of sigma dot. So now let us substitute this in this epsilon t. Okay, in this equation I have to substitute. So what did I say? Epsilon t sigma dot into t by eta plus sigma dot by r. Now I'm going to plus, it is going to be minus sigma and not plus sigma. Okay, this into, instead of t, it is going to be t minus t1 divided by eta plus sig again minus sigma divided by r. Okay, so this and this will get cancelled. This and this will get cancelled. Okay, so the remaining term will be sigma dot into T1 by eta. So this will be the response of the material, okay, at any time greater than T1. Okay. Now, if I plot for strain for this input of stress, okay, it is going to be till time, so till time T1, it is going to be like this. Okay. Now, for time greater than T1, little greater than T1, let us take it as T1 plus. What we found out, it is going to be sigma dot T1 by eta. Okay. So it is going to be here, somewhere here. Okay. Now there is a jump. So that, which means there is a jump. There is an instantaneous jump because for time t less than t1, it is somewhere here, this value. What is this value? Let us find out from this equation. So for time less than t1, what equation should be used? This equation has to be used, right? So here it is going to be sigma dot t1 divided by eta plus sigma dot by r. This is my point. Okay, this is my value at this point. Okay, for t, this is t1 minus. Okay, since these are very close values, instead of t1 minus, I'm simply substituting it as t1. Okay, so this value is going to be sigma naught t1 divided by eta plus sigma naught by r. Okay, and for a small value just greater than t1, the value is going to be sigma naught t1 by eta. Okay, which means it is lesser than this value, right? The difference here will be sigma naught by r. If you subtract these two, it is going to be sigma naught by r. This is nothing but the same value which we saw here. Why? Because it is the contribution of the spring. So when you apply stress to the material, there will be an instantaneous deformation because of the spring, and this instantaneous deformation will be immediately recovered. Okay, since it is a spring, it will be recovered immediately, and this is what is observed here. And there is going to be, so after time t greater than t1, the strain in the material is not a function of time. This, if you see here, it is not a function of time. This is a constant value of sigma dot t1 by eta. What does this mean? This strain is the residual strain. It is not going to be recovered at all. That is why this model is called as a fluid model. We saw that a fluid-like behavior will have a residual strain when subjected to a constant stress, right? So that is why this model, a Maxwell model, is a fluid model. Okay? I hope you understood this. Okay. Now I have to explain about relaxation time, and when we go to Kelvin model, I have to explain about retardation time also. But we will come back to it after we finish. So I feel that we are running out of time. So after finishing Kelvin model and Berger's model, we will come back to the retardation time and relaxation time. Okay. So if you have any doubts, please stop me in between. Okay. So let us go to Kelvin model. Okay. So let us go to Kelvin model. Now I told you that the spring and the dashboard can be arranged in any manner. In a Maxwell model, they were arranged in a series. So in a Kelvin model, they will be arranged parallelly. Okay. The properties of the spring and the dashboard are again represented by R and eta respectively. So here also, let us say I'm subjecting the material to some stress. Okay. If you see, since they are in parallel, the total deformation undergone by the Kelvin model will be the same as the deformation undergone by the spring and which is undergone by the dashboard. Okay. Then if now we have two different materials and I'm saying that both of them undergo the same deformation, which means they have to take different stresses, right? Only if they are subjected to different stresses, then they can be subjected to the same deformation since the materials are different. So here, unlike the previous case, the stress that is taken by the spring is represented as sigma s, and the stress that is taken by the dashboard is represented as sigma d, and these two, a summation of these two must be equal to the total stress which I am applying from outside externally, right? So sigma is equals to sigma s plus sigma d. So it is exactly the opposite of what we saw for a Maxwell model. Okay. Now, since I said that the total deformation should be the same as the deformation undergone by the spring and the dashboard, the total deformation is equal to the deformation undergone by the spring, which in turn is equal to the deformation undergone by the dashboard. Okay. Now, so let us first derive the constitutive equation. So how will we derive the constitutive equation? Sigma is equals to sigma s plus sigma d. We know what sigma s is. Sigma s is nothing but r into epsilon s, right? It from spring. And sigma d is equals to eta into epsilon dot from dashboard. So you can simply substitute these two. Sigma is equals to r into epsilon s plus eta into epsilon d dot. So what did I say? Instead of epsilon s and epsilon d, I can simply substitute this using epsilon. Okay, so sigma is equals to r into epsilon plus eta into epsilon dot. So this is my constitutive equation. So one thing, if you notice, there's one thing common in the spring and in the Maxwell and Kelvin model. Both the equations will be having on either side of the equation equal to sign. Okay, they will be having some constant stress and some constant stress naught, and on the other side some constant strain plus some constant strain dot. Okay, so this similarly I can add any number of derivatives as I want. Okay, maybe 3, 4. Okay, for this model it is only these two. Okay, and this is the general form of a linear viscoelastic model. So it can be, let us say, P sigma plus Q sigma dot plus R sigma double dot plus etc. is equals to A epsilon plus B epsilon dot plus C epsilon double dot plus etc. So this is going to be my general constitutive equation form for a linear viscoelastic model. So now going back, we saw that this is the constitutive equation for a Kelvin model. Now let us try to find out the response of the material when I am subjecting it to a constant stress and a constant strain. So when I subject the material to a constant strain, Just a second. I'll have water. Okay. So when I'm subjecting it to a constant stress, constant strain, since the spring and the dashpot are connected in parallel, okay, this will immediately respond. This will immediately give the required definition that I want. But to move this or to deform this dashpot, I will need an infinite stress at time t is equals to 0. Okay. So in case of a Maxwell model, it was not a problem because at time t is equals to 0, even if the dashpot took time to respond, okay, it cannot respond immediately at time t, it cannot deform immediately at time t is equals to 0. That is why at time t is equals to 0, the deformation of the entire Maxwell model was only due to the spring. But in the case of a Kelvin model, this will immediately deform. But the dashpot, which is parallel to it, will take a lot of time to deform. So there is an imbalance here, right? The strain here in these two cases has to be the same. But since the dashpot will take time to respond, this Kelvin model cannot uh, give the response of the material when it is subjected to a stress relaxation experiment. Okay, so Kelvin model cannot serve the purpose of determining the response of the stress response when subjected to a stress relaxation experiment. Now let us say I am subjecting the material to a constant stress, and this is called as a creep experiment, right? Now let us find out what will be the strain response when subjecting the material to this uh, creep, creep behavior. Okay, so let us say let me first take the equation. So it is sigma is equals to r into epsilon plus eta into epsilon dot. Okay, here sigma dot will be equal to 0, but there is no sigma dot in this equation, so we are not going to substitute it anywhere. And sigma is equals to sigma dot, so this can be substituted. So sigma dot is equals to r into epsilon plus eta into epsilon dot. So this I'm going to rewrite as epsilon dot is equals to epsilon dot plus r by eta into epsilon is equals to sigma dot by eta. Okay. Now how will I solve for this differential equation? Okay. This is the first order differential equation. First order non-homogeneous differential equation. Why is it non-homogeneous? The right hand side is not equal to 0, right? So how will I solve for this? Either so I can divide it into two parts, right? One is a characteristic function and the other to find out the particular integral, right? This is basic math. So I'm just going to apply characteristic function and particular integral method. So this epsilon dot, so this epsilon, since this is a differential equation in d sigma by dt, I'm simply going to replace this d by dt with capital D. Okay, so this I'm going to write it as d into epsilon. So d into epsilon plus r by eta into epsilon is equals to sigma dot by r. So first, let me to find out this characteristic function, I will first find out, take the left hand side of the equation. Here, let me take epsilon constant. Okay. So the okay, characteristic function of this will be c1 into e power alpha into t. Okay, t is my independent variable. Okay, see, epsilon is the dependent variable and t is the independent variable, right? So here it has to be the independent variable. If it is x, y and x, we will represent instead of t we will write it as x. Since in this equation we have t, we are substituting it as t. And what is alpha? Alpha is nothing but root of this equation. Okay, so here you will be having three forms, right? One will be the roots are real, roots are imaginary. Okay, roots are real and equal, roots are real and unique. Okay, based on that your constitutive characteristic function will vary. The equation of the characteristic function will vary. Okay, since the root is real, okay, so the root of this factor is nothing but d plus r by eta. The root of this factor is minus r by eta, right? Since this root is real and there's only one root which is unique, my characteristic function, the equation is c1 into e power alpha into t, right? So instead of this alpha, I have to substitute the root, which is minus eta by r into t. So this is my characteristic function. Now what is my so I have this is with the left hand side. Now with the right hand side, I have to find out something called as the particular integral. Okay, and this has like five cases. Okay, one case in which the right hand side is a constant. Okay, the other case in which it is an exponential function e power ax, or it is a uh, sine function, trigonometric function, or it is a polynomial. Okay, e power x power a. Okay, like that you will have many cases. What is our case now? In our case, this is a constant value, right? So ours is a constant value. So in that case, how will you solve? In that case, how will you solve? My particular integral will be equal to 1 by, just write the factor, okay, and okay, one second. So this is a constant value, right? I told you that this is a constant value. When the right hand side is a constant value, there are different ways of solving it. Now, if I in the instead of writing it as a constant value like this, so let us say some left hand side is there and the right hand side is is sigma dot by r for us, right? Instead of this I can write this as e power 0x, right? So this will also give me sigma dot by r, or I can write it in terms of say cos of 0x. Okay, so there's no separate way of solving the particular integral when the right hand side is a constant value. I have to incorporate it in terms of exponential function or a trigonometric function to solve for this case. So instead of writing it as simply sigma dot by r, I'm going to write it as sigma dot by r into e power 0x. Okay, so if it is an exponential function, so if it is an exponential function, this is how I will solve it. I will first write the factor in the denominator and write the entire function here, the right hand side here. Okay, now in the place of d, I have to substitute it by a. And what is this a? It is this value, e power ax. Okay, it is this value. Okay. it is actually not x, it is t, since I told you that t is the independent variable, right? So this d has to be substituted by this value a. For us, this value of a is 0. So it is going to be 1 by r by eta into sigma dot by r, and this e power 0t is nothing but 1, right? That is what we want. So now this will become, is this r by eta or eta by r? One second. So this will go up, right? So and this is sigma dot by eta. This sigma dot by eta, sorry. Okay. This is eta. So this is sigma dot by eta. And this eta and eta will get cancelled. So my particular integral is sigma naught divided by r. Okay, so this is my particular integral. And what is my, so what will I do with this characteristic function and particular integral? This will give me the solution of the differential equation. So when I'm substituting it to a constant stress, my response should be strain as a function of time, right? So this is my solution of the differential equation. Epsilon as a function of time should be characteristic function plus particular integral. Okay, so this will be C1 into a power minus RT by eta plus sigma dot by r. Okay, here this is my integrating constant. Now to find out this value, I have to substitute for the boundary condition, right? So what is the boundary condition here? At t is equals to 0, my epsilon is going to be 0. Why? Because I told you that in the case of a Kelvin model, okay, I'm subjecting the material to a constant stress. Though the spring will immediately deform, this dash pot will prevent it from deforming. So at time t the dashpot will take time to deform, right? So because of this, the spring will also not deform. So at time t is equals to 0, epsilon is going to be 0. So this is my boundary condition. So substitute it in this equation. So 0 is equals to C1 plus sigma dot by R. So my C1 is going to be minus sigma dot by R. So substitute it in that equation. So minus sigma dot by R into e power minus R t by eta plus sigma dot by R. Now epsilon of t is equals to sigma dot by R. I'm going to take this outside, minus R t by eta. So this will be the response of the material when I'm using a Kelvin model, okay, to predict the viscoelastic response when subjecting the material to a constant stress. Okay, so how will this look like? This is what I'm applying to the material. So at every point at any point, so at every point t, if I substitute for t from 0 to say infinity in this equation, then so this is epsilon, then the response is going to be like this. Okay, now okay, so if you see, it will approach an asymptotic value, and this asymptotic value is nothing but the deformation due to a spring into R. Okay, so this is what a Kelvin model response will look like. Okay. So now let us go to Berger's model and then come back to relaxation and retardation. One more thing. This is when the material is subjected to a constant stress. Let us say I'm going to remove the stress at some time t1. Okay. If this is what I'm going to give, then this can be represented using two uh, inputs, right? One is sigma naught for the entire time t, and at time t1 I'm going to apply minus sigma naught. Okay, so this this is what this creep and recovery experiment can be represented as using the principle of superposition. So when I do this, what will be the response of the material? Here it is going to be epsilon of t due to sigma naught plus epsilon of at any time t. If I want the response at any time t here after t1, then it is going to be t minus t1 at minus due to minus sigma naught. Okay, so in this equation, let us find out. So this is for t greater than t1. What will be the response of the material when for t greater than t1 when it is subjected to this creep and recovery experiment? Okay, so let me substitute. So for in the first case, it will be the equation as it is 1 minus e power minus RT by eta plus minus sigma naught, okay, by R into 1 minus e power minus R into, instead of t it will be t minus t1 divided by eta. Okay, now let us expand this. Okay, so this and this will get cancelled, this and this will get cancelled here. Okay, so if you see, is going to be sigma dot by R into e power minus RT by eta into e power RT1 by eta minus 1. Okay, you can check this later. Okay, check this. Now let us go to Berger's model. Okay, so and when this is what is applied to the material, okay, what do you think the response of material will be? So first it will go like this, right? And after the stress is removed at time t1, there will be an instantaneous recovery and a time dependent recovery. Unlike a Maxwell model in which there will be a residual stress, okay, after removing the a residual strain after removing the stress. In the case of a Kelvin model, there will be a time dependent recovery. Okay, if you see, it is nothing but this is the mirror image. So this part, so if you take this, flip it upside down and add it here, okay, here, this is what you will get. That is why I'm adding epsilon of t, and then at time t, I'm subtracting this epsilon of t, right? Why am I subtracting? It is sigma dot and minus sigma dot. That is why it is just taking this curve. At this point, I'm flipping it and I'm attaching it here. That is what this equation is about, right? Okay. Now, let us go to Berger's model. So what is a Berger's model? Berger's model is you will have a spring and dashpot. I told you you can have any number of springs, any number of dashpots, and they can be arranged as in how you want. So it is a spring and a dashpot arranged in series and a spring and a dashpot arranged in parallel. So this is nothing but a Maxwell model plus a Kelvin model. Okay. So how will you find out the constitutive equation for this? So this the total stress. So when I subject it to a stress of sigma, there will be a deformation in this model, and it will be summation of uh, it will be a contribution from the spring, from this dashpot, and from this entire element. So let us say this is sigma S, sigma D, and since this is a Kelvin model, and since this the deformation of this Kelvin model will be the same as this spring and dashpot here, let me write it as epsilon Kelvin. K. Okay. So this total epsilon will be epsilon S plus epsilon D plus epsilon K. Now first let us write the response due to the constitutive equation for each element. Correct? So let us say this is R1. Okay, the modulus of this spring is R1. The viscosity of this dashpot is eta 1. The modulus of this spring in the Kelvin model is R2 and viscosity is eta 2. Okay. Now let us say, let me write the constitutive equation for each element in this Burger's model. So for a spring, it is going to be epsilon S is equals to sigma divided by, let me write it as sigma S itself. Okay. So sigma S divided by, um, so this sigma S represents the stress in the spring. Sigma S divided by R1. Okay. Now you know that this is in series, right? So the total stress that is applied on the material will be the same that is being applied to the spring. So one thing which you should notice is if the stress in all the elements is constant, then they will undergo different deformations like sigma S and sigma D, sorry, epsilon S and epsilon D. In the case of a Kelvin model, the stress in each of the elements, so the deformation in each of the elements here, say let us take this Kelvin model, the deformation in each of the elements here is constant. So in that case, the stress that is taken by each of the elements will be different. Okay. So now, since they are in series, the total stress that is being applied on the material will be the same that is taken by the spring. So it is sigma by R1. Let us take sigma D. Sigma D dot. Why? Because that is a dashpot. That will be equal to sigma D divided by eta 1, which is going to be equal to sigma divided by eta 1. Okay. And now, Kelvin model, we already know the constitutive equation for the Kelvin model, so that we will write as it is. So what is the constitutive equation for a Kelvin model? Let us go back and take it from here. So it is epsilon dot plus R by, so R by eta into epsilon plus is equal to sigma divided by eta, right? So here also, this system will be subjected to, this entire Kelvin model will be subjected to a stress of sigma. But the stress taken by the spring inside the Kelvin, spring and dashpot inside the Kelvin model will be different. But the total stress that is taken by the Kelvin model is sigma, right? That is why I'm writing it as sigma here, directly as sigma here. So this is my epsilon K. Now I told you epsilon is equals to epsilon S plus epsilon D plus epsilon K. Here, if you see, it has these differential terms, right? These differential terms. Now, how I cannot simply add them, right? So even if I take just like we took for Maxwell model as epsilon d is equals to epsilon s dot plus epsilon d dot, I cannot do this for epsilon k dot because if I take this epsilon k dot, I will take everything here to the right hand side, right? And then again, I will be having an epsilon k term. Only if there is no epsilon k term here, I can simply take these equations, these terms to the right hand side, and I can simply add them here. But here, I have an epsilon k term. So how will I solve for this equation? How will I get the constitutive equation here? Okay. So here, I can simply use the Laplace transform. Okay, so what is a Laplace transform? So I'm going to use Laplace transform. So whenever I have a differential equation or an integral equation, to make the equation easier, I'm going to use Laplace transform. So what will this Laplace transform do? So whatever is there in terms of this differential form, okay, the differential equation, I will rewrite in such a manner that it will become an algebraic equation for me so that I can easily work with it. Okay, and then if I do the inverse Laplace transform, it will again go back to the differential form. So that is why we use this Laplace transform. Now, let us say my epsilon s is this. Epsilon s, I need not apply any Laplace transform, or even if I apply Laplace transform, it is not going to be of any change because it does not have a differential operator to it. Okay. Now now let me take this second term, which is epsilon d dot. This is going to be sigma by eta 1. Okay. So this epsilon d dot, if I take Laplace transform, I can represent this as s into epsilon d. So here epsilon d will be a function of t, time, right? So when I take Laplace transform, it will become a function of s. Okay, so this is what you need to know about. So if you want to know more about Laplace transform, you can always go to YouTube or Google about it. Okay, but in order to make things simpler for you, I'm simply going to say that instead of this um, epsilon dot, this dot is just replaced by s. Okay, if it is double dot, it will be replaced by s square. Okay, s square epsilon. So this is what this Laplace transform does. So this s into epsilon d is going to be sigma by eta 1. So what I need only epsilon d. So I will rewrite it as sigma by s into eta 1. Now I have epsilon k. So here this epsilon dot k, right? I can write it as s into epsilon k. S into epsilon k plus r by eta into epsilon k is equals to sigma naught by eta or sigma by eta. Alright. Now I will take epsilon k common. R by eta. So this will be R2 eta 2. Right? So epsilon k will be sigma by eta 2 divided by s into, sorry, s plus R2 by eta 2. Okay. Now I have three terms without any differential operator, right? So I can simply add them now. Epsilon is equals to epsilon s plus epsilon d plus epsilon k, which will be sigma dot by r, sorry, sigma by r, r1 plus sigma by s into eta 1 plus sigma by eta 2 divided by s plus r2 by eta 2. Okay. Now I will take LCM. Denominator will be r1 s into eta 1 s plus r2. Okay. Uh, this I'm taking so this I'm taking an LCM of this and I'm taking this up. So this eta 2 and eta 2 will get cancelled. Okay. And this s will be multiplied by eta 2. That's all. And this will be, so if I take LCM, it is going to be s into eta 1 into sigma into s plus r2 by eta 2 plus sigma into r1 into s plus r2 by eta 2. So how am I getting this? Multiply throughout by this LCM. Okay, so now I have this LCM. this LCM term, each term you multiply that by this LCM term. So what will you get? So for this sigma, R1 and R1 will get cancelled. When I multiply it by this, okay, this and this will get cancelled, and the remaining terms will get multiplied with this sigma. Okay, so this is basic math. Here also, S and eta 1 will get cancelled, and the numerator will get multiplied with R1 here, which is this one, and this term. Similarly, plus sigma, okay, this eta 2 is already cancelled. So sigma into R1 into S into eta 1. So this is my epsilon. So if you rearrange the terms, okay, you will get sigma into R1, R2. So I'm not going to write step by step, I'm just going to write the final step because we are running out of time. Okay, if you want, you can solve it and see later. Okay. Now, to get the final equation which Sir showed, okay, you have to divide it by R1, R2. Okay, so when you do this, you will get sigma into sigma S, eta 2 divided by R2 plus eta 1 divided by R2 plus eta 1 divided by R1 plus eta 1, eta 2 divided by R1, R2 sigma S square is equals to epsilon S square eta 1, eta 2 divided by R2 plus epsilon into S into eta 1. Now, what did you do? You had a differential equation. Had you, so working with it was difficult, so you took Laplace transform and wrote sigma dot s into sigma dot and epsilon dot s into epsilon dot. And when you did that, all you did was basic algebra. So you just took LCM, multiplied, took LCM, multiplied it, divided it, rearranged the terms, and you got this equation. Now what you have to do, if you have to get the constitutive equation, this is not the final equation. Why? Because it is in terms of s, which means the Laplace transform has been applied. Now you have to apply the inverse Laplace transform. This is very simple. What you will do, instead of s into sigma, you will replace s into sigma by sigma dot. You will replace s square into sigma by sigma double dot. Okay, that's all. So if you see, it is going to be okay. So I will just write it here. So this will be epsilon dot, and this will be this will be epsilon double dot because it is epsilon s square, and this will be epsilon dot. Okay. So this is a linear viscoelastic model, right? And what did I tell you? The form of the linear viscoelastic model will be like this. We saw, right? P into sigma plus q into sigma double dot. Yeah, like this, right? Same thing goes here. Here also you have a term with sigma, sigma dot, sigma double dot. Here you do not have the epsilon term, but you have epsilon dot and epsilon double dot. The coefficient of epsilon term here is 0. So that is what the Burgers model, that is how you will get the equation for the Burgers model. Now I'm not going to explain how things will be solved here, since this is a second order differential equation, okay, and it has two variables, sigma dot and epsilon dot. So you need 2 plus 2, 4 boundary conditions. Okay, and the boundary conditions, it is given by Sir. Like Sir has already explained the boundary conditions. So we are not going to go further into this. Now, so last half an hour I'm going to dedicate it to solving problems. So in 10 more minutes, I'm going to explain about other models. Okay. So here we saw a Maxwell model, Kelvin model, and a Burgers model. So a viscoelastic model, you know that a viscoelastic material can show a viscoelastic solid-like response or a viscoelastic fluid-like response. What do I mean by this? If it is a solid-like response, then it is more inclined to have more of the elastic properties, and if it is a fluid-like material, it will have more than 50% more of fluid properties, right? Now, a model can also be used to explain this behavior, which means I can have a viscoelastic fluid model to represent the response of the material, which shows a viscoelastic fluid-like properties, or I can have a viscoelastic solid model to represent to determine the response of the material when it shows a viscoelastic solid-like response. Okay, so if you see a Maxwell model, is it a fluid model or a solid model? It is a fluid model. Why do I say so? It has a dashpot hanging separately, which means when I remove the um, when I remove the stress, it is going to have a residual strain because of this dashpot. Had it been connected in parallel, okay, this also has a dashpot. But if it is connected in parallel, then the spring will somehow make sure that the dashpot, that the residual strain is zero. Okay, so it will try to bring the dashpot to a zero. So a Kelvin model is a solid model, and a Maxwell model is a fluid model. So if you see a Burgers model, do you think it is a solid model or a fluid model? It is a fluid model. Why it is a fluid model? Though it has a Kelvin element to bring this deformation to zero, it has a dashpot hanging separately, right? It is all alone. So when the stress is removed, there is going to be residual deformation because of this dashpot. Okay. And Burgers model, we saw that, so I would have explained that the response is going to be like this, right? So this is what we want from a typical viscoelastic. This is what we expect a model to show, like instantaneous jump, then delayed creep, then instantaneous recovery and a delayed recovery. So this is what we want. Okay. Now let us. So now there are like this. I have two elements. Actually, there are other elements also, but here we are going to confine ourselves only to two elements, and these can be any number can be added in any combination, right? So in that manner, what we saw a two parameter model. What do I mean by a two parameter model? A Maxwell model and a Kelvin model, because it had only two elements with two parameters. So each element has one parameter, a spring and a dashpot. Dashpot each had one parameter, so it is a two parameter model. In the same way, a Burgers model is a four parameter model because it had four elements and correspondingly four parameters. Similarly, I can have three parameter models also. Say I can have a spring, okay, in series with a Kelvin model. So this will be a solid model. Why is it a solid model? Because it has a spring. Okay, and here also the deformation will be brought to zero. Here also the deformation will be brought to zero once the stress is removed. Okay, there's one more model called as, so there are many models. I'm just giving you a few examples. This is a fluid model, viscoelastic fluid model. Okay, so this here, even even if I remove the stress, there's going to be residual deformation because of this dashpot. So this is a viscoelastic fluid model. All these are three parameter models. In the same way, you can have this model also. You can have a Maxwell model like this, okay, along with a spring. Okay, so here it is a Maxwell and a spring, both are in parallel. In the same way, a Maxwell model again with a dashpot. Here also, this is a fluid model. Why it is a fluid model? Here there's this spring cannot bring the deformation to zero because of this dashpot. Okay, here the deformation can be brought to zero because of this spring. Okay,
So this is how various elements can be arranged. And in addition to this, you can have something called as a generalized Maxwell or Kelvin model, which means I can have any number of elements, and let us say I can arrange several Maxwell elements in a series or several Maxwell elements, okay, in parallel. Okay, so this is called as a generalized Maxwell model. This is a Maxwell model generalized Maxwell model connected in series, and this is a generalized Maxwell model connected in parallel. Similarly, for a Kelvin model, you can have several Kelvin models connected in parallel, okay, or you can have several Maxwell models connected in series. The constitutive equation for this, if you want, we can derive it next class or maybe after this session if time permits. Okay. So first we will go solve the problems and come, and then we will come back and solve. We will see if we can solve for the retardation time, relaxation time, and this generalized Maxwell and Kelvin model. If not, before starting tomorrow, next week's session, we will finish off with generalized models, retardation and relaxation time, and then move on to the next week's session. Okay. So in addition to this, um, one more topic which was explained this week was small amplitude oscillatory shear. So I wanted to show you an animation of how this experiment is actually performed. Okay. So as the name says, it is a shear experiment and it is an oscillation. So what does this mean? The So this shear is applied on bitumen. So this is the bitumen sample, this black material. It is sandwiched between two plates, and and the plate is and the top plate is oscillated in a sinusoidal manner. Okay. So if you see here at point A, the plate is in this position, then it will go to the left. Okay, sorry, it goes to the right here, point B, then it again comes back to point C, which is the main position, and then it goes to the other direction D, okay, and then it comes back to E. So this B and D, okay, the extent to which it goes, it can go to this position, it can go to this position, it can go to here, okay, the extent to which it goes on either side of the main position, that is called as amplitude. Okay, and how fast this plate oscillates. Okay, so if you see, maybe this to complete one cycle, maybe it takes 10 seconds now, sorry, 0.5 seconds now. Now it can this oscillation can be completed in zero point 0.1 seconds also, or it can be completed in 10 seconds also. So that time duration taken for the player to complete one complete oscillation, which is one complete cycle, is called as frequency. Okay. So if I say that the frequency is 1 hertz, it means that one cycle gets completed in 1 second. If I say my frequency is 10 hertz, then one cycle gets completed in zero point 0.1 seconds, which is 1 divided by 10. Okay, so this is what a small an oscillatory shear experiment is. Okay, and the input parameters which you give for this experiment are uh, amplitude and frequency. And since the most commonly controlled parameter in an oscillatory test is strain, you will give strain, amplitude and frequency. Okay. If it is a stress controlled experiment, you will give stress, amplitude and frequency.
Okay. So this animation I wanted to show you. So now we will go to the questions. So a Maxwell model will exhibit, okay, we saw what a Maxwell model is. So will it exhibit constant strain rate during loading? So let me first draw it. Okay. So since we are talking about a creep and recovery experiment, and I'm showing the response of the material when subjected to creep and recovery experiment. So constant strain rate during loading and recovery in a creep and recovery experiment, increasing strain rate during loading. So I told you that this line is a constant and it has a slope of sigma dot by eta. Okay. Since the slope is constant, the slope is the slope of a strain curve. So slope is constant means strain rate is constant, right? Because the slope is nothing but the strain rate. So from these four options, either it has to be this or this, right? So it does the strain rate does not keep increasing during loading, but it remains constant. Now, after recovery, what happens? So after recovery, the strain is constant, which means the strain rate is zero actually, right? So zero can also be said as, sorry. So zero, yeah. So zero can also be said as constant. Zero can also be constant. So before loading, strain rate is constant, and after loading, strain rate is zero, which is also constant. So here it is going to be this option because the other option says it has a decreasing strain rate during recovery. Right. So that is not the answer. So pick the correct option with respect to cone and plate geometry. So let us come back to this. Okay, when we first let us finish the questions on modeling. Now, what is the distinction between relaxation and recovery? Okay. So, uh, what is relaxation? When do we call a material? When we say that, when will we say a material to relax? Material will relax only when it is subjected to a constant strain. Okay, till the stress will relax. Okay, so relaxation means relaxation in stress. Okay, with time when it is subjected to a constant strain. Okay, or a step function strain in time. Okay. Now, what is recovery? So when I remove this strain, this stress, okay, will go back to the other side and start recovering. Okay. So either the stress will recover or the strain will recover. So relaxation corresponds only to stress response when subjected to a constant strain, whereas recovery refers to the response when it is subjected when either a stress is removed or strain is removed. So when a strain is removed and the stress recovers, a stress response, you will call that as recovery. Or when a stress is removed and the strain recovers, okay, you will call that also as recovery. Sorry, you will call that also as recovery. Okay. So the answer to this will be this. Relaxation is the stress response in time to an applied step function strain, okay, and recovery is the response following the removal of an applied stress or applied strain. Okay. Now, oscillatory shear testing of bitumen is used in what? First question is, it is used in the performance grading of bitumen. So all of you must be aware of what performance grading is, right? So here we subject the sample, a disc-like sample, to oscillatory shearing, and we measure storage, like the shear modulus, okay, the absolute value of the complex shear modulus, okay, complex modulus, mod of the complex modulus, and we measure the phase angle, okay. So phase angle and modulus, that also we did not cover this week. So maybe we will cover that also next week. Okay. And we will measure, so we will measure these two values and find out if the criteria, which is G star by sine into sine delta or G star by sine delta, a particular criteria is satisfied. Okay, maybe when we go to performance grading, so this course will have performance grading as well. When we go to performance grading, we will know better. So it is used in the, so for performance grading of bitumen, we will use oscillatory shear testing. Then determining the mixing and compaction temperature of bituminous mixture. So most of us would have heard of uh, determining the compaction temperature using a rotational viscometer, right? But in some cases, we also use a dynamic shear rheometer and test on a parallel test using a parallel plate system, okay, where we find out the delta where it approaches to 90 degrees Celsius. See, sorry, 90 degrees. Sorry, the delta approaches to 90 degrees. Why it should approach to 90 degrees? Because at 90 degrees, the material is expected to show a viscous response. And for mixing and compacting, we want the material to show a viscous or Newtonian response for evenly coating the aggregate particles. So it is also used for determining the mixing and compaction temperature of bituminous mixtures. Bitumen in bituminous mixtures. Okay. And aging characteristic prediction of bitumen. Yes, it is used for aging characteristic prediction of bitumen. Okay. So in this testing is used for all the above three cases. Just a second. Okay. So the next question is pick the correct behavior of Berger's model. Now, in the models that we saw today, both Maxwell and Kelvin model, we applied a constant stress or constant strain, which is a time domain testing, right? So with time only, the stress or strain varied, and we measured the strain or stress response with respect to time, right? Now, uh, this using this model, we can also predict the response of the material when it is subjected to oscillatory loading. Okay, so that also we did not see. Um, so when it is subjected to oscillatory loading, um, both in all the three cases, a Burger's model, Kelvin model, or Maxwell model, um, Padma ma'am would have explained how the material parameters, either it could be uh, sorry, the material parameters, not model parameters. Either it could be modulus or delta or storage modulus or loss modulus, how they vary with frequency. Because it is a frequency domain test, we plot it against frequency and find out how it varies, right? So in the case of a Burger's model, the question is how the phase angle varies. Okay, so this curve represents the response of the material, okay, um, when it is subjected to oscillatory loading. And here, log of tan delta shows how the curve shows how it varies with frequency. So if you see, first it decreases, then it reaches a kind of a constant value, and then it in it increases and again decreases. So you just have to pick from these statements uh, which sounds correct. Okay. So tangent of phase angle is independent of frequency. If it is independent of frequency, it has to be constant with it has to be a straight line, right? Second is tangent of phase angle increases with increase in frequency. So this statement itself is wrong because in both the cases it decreases. Now again, tangent of phase angle decreases with increase in frequency. So with increase in frequency, it decreases. reaches a rubbery state, and the phase angle decreases with further increase in frequency. So it can be either tan of phase angle or phase angle. So both will refer to the same. Okay. So this seems to be the correct option. Now moving on to the next question, which is which model is suitable to find the range of retardation and relaxation time of viscoelastic material. So we did not see what a relaxation time or retardation time means. So this term will come only when the model has a dashpot. Okay. Only when it has a dashpot, it will have a retardation. So this only contributes to the viscous nature of the material, right? And this um, time-dependent characteristics is introduced due to the viscous nature of the material. So it is a contribution of the dashpot. So how many dashpots it has, that many number of relaxation times the material will have. So if you see the Maxwell model will have one relaxation or retardation time. Relaxation time is when the material is subjected to a constant strain, and retardation time is when the material is subjected to a constant stress. Okay, so when you subject the material to a constant strain, the stress relaxes, right? So the time taken for the stress to relax is taken as the is called as the relaxation time. Similarly, when you subject the material to a constant stress, it uh, so Maxwell model does not perform well in case of a creep and recovery test. Okay. So let us say for a Kelvin model, so it reaches an asymptotic value, right? So in that case, um, the time taken for the material to reach this asymptotic value is called as the retardation time. So either this relaxation or retardation time is a contribution of the dashpot. And how many number of dashpots you have, that many number of relaxation or retardation times you have. So for a Kelvin model and a Maxwell model, you have only one relaxation or one retardation time. Okay, in case of a Burger's model, you have two dashpots, right? So you have two relaxations or two retardation times. Now, if you have so if you want a range of relaxation times or retardation times, then you have to have many number of dashpots. And we saw that which model has many number of dashpots? A generalized model, a generalized Maxwell model or a generalized Kelvin model has many number of dashpots because it is many number of Maxwell or Kelvin models added in series or in parallel. So the answer to this is generalized model. Okay. So the next question is a void Kelvin model will exhibit stress relaxation and creep recovery as expected for a typical linear viscoelastic material. So when we saw this Kelvin model, I explained one thing. When it cannot be subjected to a stress relaxation experiment because the dashpot will not respond immediately to the strain which is being applied. So in that case, it will not respond well to a stress relaxation experiment. So out of these, just eliminate stress relaxation. So it will not exhibit stress relaxation. So there's only one option. So there are two options. It will. So this also will not exhibit stress relaxation, and this also will not exhibit stress relaxation. But will it exhibit creep recovery, creep and recovery? Yes. Compared to a Maxwell model, this will exhibit a good creep and recovery behavior, just like we expect from a linear viscoelastic model. So it will exhibit good creep and recovery behavior. Okay, so this is creep and recovery behavior, but not a stress relaxation behavior. So the answer to this is will not exhibit stress relaxation, but predicts creep and recovery as predicted as expected for a typical linear viscoelastic material. Select the geometry that most suits to test the Newtonian material. So in a DSR, there are three geometries. One is a parallel plate system, which means the top and bottom are parallel plates. Okay, the material is sandwiched between two parallel plates. This is called as a parallel plate system. The other is a cone and plate geometry. Okay, so the top plate is in the shape of a cone, the bottom is a plate.
and the material is sandwiched between these two. So this is a cone and plate geometry. And one more is a concentric cylinder, okay, in which there will be a cup and a bob. So this helps in finding out the viscosity of the material. Okay, so you apply rotation using this bob, okay, and the cup remains stationary. In some cases it can be other way around also, but in a dynamic sperriometer we apply rotation to this bob and the cup remains stationary, and based on how the fluid around the bob gets displaced, okay, the viscosity can be measured. And this is very much suitable for a Newtonian material, because a Newtonian material um, will be flowy, right? So it has to be contained within a cup. It cannot be contained in a so if you try to sandwich the material, a Newtonian material, between two plates or a cone and plate, when load is being applied, it will ooze out. Okay, it will not it will not stay here. It will not be confined. So in order to confine the material, you have to have the material in a cup suspended with a bob. Okay, so the geometry which is most suitable is a concentric cylinder. If you have any questions, please post in the discussion forum. Okay, regarding this, please post in the discussion forum, or reply to the or add as comments below the YouTube video. Okay, and the next is the magnitude of complex shear modulus. So here nowadays we are replacing, at least in our lab, we are replacing. So what is complex shear modulus? Complex shear modulus is storage modulus plus loss modulus. Okay, it is a complex number, right? And if you take mod of this value, okay, so this is called as mod of complex number. Okay, so complex shear modulus. Okay, and people used to call it, earlier we kept on calling it as dynamic modulus, but nowadays, since dynamic modulus is more suitable. So people usually call this magnitude of complex modulus as dynamic modulus in the case of bituminous mixtures. So there was always a doubt as to whether as to what should be called in the case of a bitumen. Why we are differentiating it in terms of bitumen and mixtures is the type of loading in these two cases is different. In mixtures, we will apply tension or compression, axial loading. Okay, whereas in the case of bitumen we will apply shear. So when we submitted our work, okay, to any journal article, the review comments, the most of the reviewers kept asking, why do you call it as dynamic modulus for a bitumen? Because dynamic modulus is usually used to represent the modulus for mixtures. So what we did, we replaced this term dynamic modulus by absolute shear modulus. Okay, we refer to a guideline, okay, where they had represented this as absolute shear modulus, and nowadays we are calling this complex shear modulus, the magnitude of this complex shear modulus, as absolute shear modulus for bitumen, and dynamic modulus in the case of mixtures. Okay, so in an oscillatory shear, when the bottom plate is fixed, the velocity of the plate sticking to the top plate is, and that at the periphery is what? So let us take a parallel plate system. In the case of a parallel plate system, only this plate will oscillate. Okay, this will remain stationary. Now, when the material is sandwiched between these two plates, the bottom okay, the bottom plate, the material which is sticking to the bottom plate will have velocity as 0. The material which is sticking to the top plate okay, will have some velocity, but it will not be the same throughout. Why? Because it is a circular plate, okay, and each plate, so each so the particle at each radius will be subjected to different motions. Say, let us say I'm oscillating the plate to this extent, okay, the plate in the periphery will be subjected to this much distance, whereas the plate at this radius will be subjected to only this short distance, which means the plate at the particle at the center of the plate will be subjected to a velocity of 0. So even if I take the top plate, I simply cannot say that the material is that the material sticking to this top plate is subjected to a velocity of v. Okay, unlike a translatory motion, since this is a rotational motion, okay, or oscillatory motion, the um, velocity at the center of this plate sticking center sticking to the top plate is 0, whereas at the periphery it is maximum. Okay, so if you see, with respect to height, the velocity will be, here it will be 0 in all the places, and with increase in height there will be an increase in velocity. So the velocity will be maximum at the top plate. But even at the top plate, at the center of the top plate, okay, this is top view. At the center of the top plate, the velocity will be 0 and the velocity will be maximum at the periphery. Okay, so that is what I've asked. The velocity of the particle sticking to the top plate is maximum, okay, and that at the periphery is maximum. So what I asked is top plate and periphery. So top plate and periphery is maximum. Had I asked top plate and center, then it would have been 0. Okay, it is just one value. Okay, let us say uh, sticking to the top plate and that at the periphery. Okay, it is just one location, top plate, periphery. Okay, whereas top plate and center, so top plate can be any position, right? So in this question I want velocity at the periphery, whereas now I'm giving you a question, if had I mentioned center, then the velocity would have been 0. Okay, so let us move to the next question. In a Burger's model, the instantaneous strain observed during creep and recovery is captured by what? So we saw it is a combination of a Maxwell model and a Kelvin model, right? So it will have an instantaneous jump, okay, and an instantaneous recovery. Both will be contributed by this Maxwell spring. Okay, so this you have to know. If you see that figure, you will understand. If you see that figure and if you solve for that equation, you will understand. So it is because of the spring present in the Maxwell element. Now, um, so coming to a small amplitude oscillatory shear experiment, there are many ways of testing the material. So I said that we subject the material to oscillation, a sinusoidal oscillation with a amplitude and a frequency, right? Frequency, let us call it as omega. Okay. Now I can play around with these values and probe the material in any manner. Let us say I can keep on increasing the frequency. Okay, frequency is in time t, I can run one cycle and then I can keep on reducing the frequency. Okay, see the time duration to complete one cycle, it keeps on reducing, which means I am increasing the frequency here because the time taken to complete one cycle keeps on decreasing here. So this is called as a frequency sweep test, which means with increase in time, I'm playing around, the amplitude will remain the same. Okay, in all the cases the amplitude will remain the same and I'm changing the frequency with time. So had this completed in 1 second, this would have completed in 0.9 second, this in 0.8 second. So this is called as a frequency sweep experiment. I'm keeping the frequency as a constant and I'm the amplitude as a constant and I'm varying the frequency with time. Or I can subject it to a amplitude sweep experiment. Amplitude sweep is I will keep the frequency as a constant and I will keep changing the amplitude. Okay, so the amplitude keeps increasing. This is called as an amplitude sweep experiment. So I can play around with these two values and I can either perform an amplitude sweep test or a frequency sweep test. Now, when I perform a frequency sweep test, okay, so if you see, you know that G dash represents storage modulus or the elastic component and G double dash represents loss modulus or the viscous component, right? So um, when I do this, when I do this experiment, this storage modulus, this can be more understood when we go to time temperature superposition principle. But first understand, so let us first understand that when I, when I, when the frequency is more, okay, the material will give a solid like response, which means this component will be more. When the frequency is less, okay, the loss component, the viscous component will dominate, so G double prime will be more than G prime. Okay, since they are related to each other, either this will be more or this will be more. And there will be a particular point, particular frequency at which this G prime will be equal to G double prime. The values will be the same. So at that point, we call that point as crossover frequency. It is the point at which if you go to one side, either G prime will be more or G double prime will be more. If you cross and come the other side, it will be the opposite. So it will be like this. If you plot G prime versus G double prime, they will be crossing at a point. Okay, so one is G prime and one is G double prime. So which is, this is frequency. Let us say I'm plotting both G prime and G double prime. So which is G prime here? With increase in frequency, my G prime will increase, and with decrease in frequency, my G double prime will increase, because decrease in frequency contributes to viscous component. Okay, so this point is called as the crossover frequency, and you know that phase angle, okay, is given as tan inverse of G double prime by G prime. Okay, so this is the phase angle. We saw phase angle, right? The phase shift between a stress and strain curve. So this is given by tan inverse of G double prime by G prime. So if these two are equal, then tan inverse of 1 will be equal to 45 degrees. So at crossover frequency, G prime will be equal to G double prime and the phase angle will be equal to 45 degrees because they are equal. Okay. Now moving on to the next question. The selection of frequency of testing for bitumen is more related to what? So frequency is related to time. Why? Frequency is the inverse of time and time refers to the speed of travel. Okay. So here frequency is related to speed. How am I saying this? So ma'am also would have mentioned that a vehicle traveling at 80 kilometers per hour, if the contact length is 2.2 meters, then it will take, so this is speed and this is distance. From this you can calculate the time, which is, so the point of contact will be zero point 0.1 seconds. Okay, to cross that distance, it is going to take zero point 0.1 seconds at this speed. So if this is the speed, I can get frequency as 1 by inverse of time, right? So the frequency is related to the speed of the vehicle. Okay, so here it is speed. So moving on to the next question. Storage modulus is the dash and loss modulus is what? So storage modulus, we saw that G dash is equal to G prime plus I into G double prime. Okay, so this is the cos component and this is the sine component, right? So uh, this cos means, so it is actually like this. If this is my G prime and this is my delta, which is my phase lag, so this will represent the in-phase component, cos, okay? So it is nothing but G star cos delta, and this will represent the
out of phase component, which is G star sine delta. So you know that G prime refers to elastic modulus or elastic response, and G double prime refers to viscous response. And also cos means it is in phase component, and sine it is out of phase component. Okay, so the answer to this is this. Now, if the phase angle for a bitumen sample at 40 degrees Celsius is 54 degrees, then which among the following holds good for this case? So, phase angle is 54 degrees. What did we see? If phase angle is 45 degrees, it means G prime is equal to G double prime. Now, you know that when phase angle is 0, material is elastic. Phase angle is 90, material is viscous. So let us say my phase angle is this. 0 means elastic, 90 means viscous, 45 means it has both elastic and viscous properties equally. So let me take a new slide. Sorry. Okay. Elastic, viscous, 0 degrees, 90 degrees. This is 45 degrees. So here, more than 45 degrees, my G prime will be more than G double prime will be more than G prime because the viscous component will dominate. Only then, when it nears 90 degrees, it will be entirely viscous, right? Here, my G prime will be greater than G double prime because my elastic component will dominate. Only then, when it nears 0 degrees, it will be entirely elastic. So, when the material response is 54 degrees, okay, when the phase angle is 54 degrees, what does it mean? The storage, the loss modulus. So what did I say at this point? It is loss modulus is more than the storage modulus. Okay. So if loss modulus is more, it means that the fluid-like properties are more. So if you see here, loss modulus will be higher than the storage modulus. Sorry, here, indicating fluid-like behavior. Okay. Okay, there's something wrong. I'm not able to erase, but this is not the answer. This is not the answer. I don't know how it got picked. So this is the answer. Okay. Now moving on to the last question, or we have one more question, right, related to regarding cone. Okay. In stress control test, if this is my stress input, which means this is my stress input, okay, what will be my strain response? Last class itself, we saw that whatever be the input, the stress will always lead, will always come first, and the strain will always follow the stress. Okay, so my strain will start here. Okay, this is my strain. So this is my phase lag. Okay, so this will nothing but gamma dot. This will be the amplitude of this wave sine omega t minus delta. Why? Because it is a lag. Okay, so the answer to this will be this. Okay. Now one more question, last question. Pick the correct option with respect to cone and plate geometry. So when I explain the parallel plate geometry, okay, I said that with increase in radius, let me give a top view. With increase in radius, my shear rate will vary because my velocity is different at different points. Okay, it will vary with radius. Similarly, with increase in height, this is the side view. With increase in height, my shear rate will vary because my velocity will increase with increase in height. So now what has happened here? With increase in radius, the height is not constant, but this is also varying. So this has been formulated in such a way that the change in the shear rate because of the radius is compensated by this change in the shear rate with respect to the height. So the shear rate will remain constant with radius. Okay. So with radius, the height is varying, right? So what will happen is whatever change is happening with respect to the radius will be compensated by this change in height. So the shear rate will remain constant with radius. So this is all for today's tutorial session. So if you have any doubts,
Please feel free to text. Okay. So I will stop sharing and we will end the session. Thank you.